Good morning, all. Today we'll start the discussion on Hahn-Banach theorem. So before we do this, we need to recall what is known as Zorn's lemma. So I'm sure all of you must have seen Zorn's lemma sometime and an application of that. For example, like when we prove that every vector space has a basis, then we need to use Zorn's lemma. So let me just briefly recall what is Zorn's lemma. So first, we'll recall what is known as a partial order set. So a set with a relation we'll denote it by less than equal to is called a partially ordered set. If this order satisfies three properties. One is x is less than equal to x for all x. Let's call this set as capital X. So this is called reflexivity. Second is transitivity. So if x is less than equal to y and y less than equal to z, this implies x is less than equal to z. That means this ordering is transitive. And the third one is antisymmetric. So if x is less than equal to y and y is less than equal to x, then this implies x is equal to y. This is antisymmetry. But here we are not saying that if we have any two elements, then there may not be any relation between them. So if I have x and y, it is possible that neither x is less than equal to y nor y is less than equal to x. Right? So that's why it's called partially ordered set. And suppose I have a partially ordered set, then what do we mean by a chain or totally ordered set on this? So or this is also called totally ordered subset. So a subset Suppose I write a subset C of X is called a chain if so it has this property that any two elements can be compared. So if A and B belongs to C, then either A is less than equal to B or B is less than equal to A. Right, so this may not be true for partially ordered set, but if there is a subset which satisfies this, then that set C is called a chain. So for example, if you take any set X, so if let's say uh, capital A is any non-empty set, and suppose I take X to be equal to the power set of A. This is all subsets of A. So X is consists of all, say, B says that B is a subset of A. So then on this one, this subset, this relation is a partial order on X. So here we will write if we have any two subsets, then we have B1 is less than equal to B2. This means B1 is a subset of B2. So you can see here that you may have two elements such that neither is a subset of the other. So in that case, they cannot be compared. But this satisfies the reflexivity, transitivity, and antisymmetry. So therefore, this becomes a partially ordered set with this subset relation. And suppose I have, so suppose X with some partial order. This is a partially ordered set. And suppose I have some subset of this. So S is a subset of X. So we say, let's call some element x naught belonging to x is an upper bound for S if for every element, so we have S is less than equal to x naught for all S belonging to capital S. Right, so upper bound again is the usual definition that if it is bigger than equal to every element in this set, then we call that an upper bound. But this upper bound need not belong to the set S. Right? So x naught is an upper bound. So just like for real number, we define upper bound for a subset. Similarly, we can define for any partially ordered set an upper bound. And we can also define maximal element. So, an element is called M belonging to X is called maximal element if there is no element which is bigger than this. So that means that if suppose I have some element which is bigger than equal to this, so if M is less than equal to A, for some A belonging to X, then this A must be equal to M. Right? So a maximal element means that uh, there is no element which is strictly bigger than this element M. So note that we can have many maximal elements for a partially ordered set. We have more than one maximal element. So these are all simple definitions. Now we can state the Zorn's lemma. So this says that if every chain in a non-empty partially ordered set X has an upper bound, then X has a maximal element. So this John's lemma, this is equivalent to the axiom of choice of set theory. So if you assume axiom of choice, then you can prove John's lemma. And John's lemma also implies the axiom of choice. So I'll just write this remark. John's lemma is equivalent to the axiom of choice. So this John's lemma is a very important tool to prove the existence of something. So for example, for any vector space, if you want to prove that there is at least one basis, then what we do is that we basically we prove that there exists a maximal linearly independent set, and then it is easy to prove that a maximal linearly independent set uh, is the basis. So for that you look at the so basically you will have to use John's lemma to prove that there is a maximal linearly independent set. So for that you have to prove that if there is any chain, then it must have an upper bound. So you look at the collection of all linearly independent subsets, and then you can give the usual partial order by subset relation. So then if I have any chain in that, then you can simply take the union of that will become an upper bound, and therefore by John's lemma there exists a maximal element, so that will be a maximal linearly independent set, and then you can show that maximal linearly independent set has to be a basis. Similarly, in many other places you might have seen that by using John's lemma you can prove the existence of certain things. So
Sir, is
yes,
this like axiom of choice, like you mentioned, it's equivalent to John's lemma, but like is axiom of choice like well accepted in mathematics community, or like is there some debate or something? Because I've
yeah,
read some paradoxes like Banach, Tarski
yeah,
paradox.
exactly. So see, that is a big discussion. So, this axiom of choice, like there are like many, since if you study about set theory, so there is this what is known as Zermelo-Fraenkel axioms. So those are like basic axioms that we assume uh, for set theory, but those axioms they do not imply this axiom of choice, which seems very like obvious. Like what does axiom of choice says that if you have a non-empty collection of non-empty sets, then uh, you can choose one element from each of them, right? So it seems very like obvious thing that okay, if you have uh, say x alpha, for each alpha, x alpha is a non-empty set, then the axiom of choice simply says that there exists a small x alpha belonging to capital X alpha for every alpha. So for this, mostly, I mean, this is the well accepted that axiom of choice is assumed to be true, and in like almost all of mathematics, you will see that we use it without any like we take it for granted basically, but I mean there are some branch like where like people try to see whether like things are true without axiom of choice or not, and then there are these things that okay, this thing, like if you don't assume axiom of choice, then you cannot like you can have a vector space without a basis, and then many things will go wrong that we prove by using this axiom of choice. So those things will, but this is I mean without axiom of choice also we have like a consistent set theory. So therefore this is not something that one can prove. So we are saying that John's lemma is equivalent to axiom of choice. There is another axiom which is like equivalent to this, which is called well ordering principle. So that says that given any non-empty set, there exists a well ordering on that. So what is well ordering? That says that if you take any in non-empty subset, then it has a minimum element. So, or this well ordering principle, if you do think, that is very counterintuitive. Though axiom of choice is intuitive, like well ordering principle, if you want to assume, then that means that on R you can define a well ordering, but explicitly you cannot like see like how to define a well ordering on R. So that says that if you take any subset, then with respect to that ordering, there will be a smallest element. So so that is that way you can say that it's not something that if someone says axiom of choice, people will say that yeah, there's nothing to prove, it is obvious, but so,
Yeah,
so
and also like I've heard about this Banach-Tarski paradox that you can take a sphere and cut it into pieces and then rearrange it to get a
right,
larger sphere, and
yeah, so you
that
can
will
get
follow
pair of
laws.
a double volume, so that kind of thing. So the thing is that the way that can be done, now it involves non-measurable sets. So the thing is that if like uh, you think of these like volumes, basically we define Lebesgue measure, right? So oh, there like what you assume that this Lebesgue measure, like if you have Lebesgue measure of disjoint union, countable disjoint union, should be equal to the sum of the Lebesgue measure of the individual pieces, right? So, oh, but this thing is not true. Like if you have studied about outer measure on Rn, then there we don't have that subadditive, that additivity property. So the thing is that Banach-Tarski paradox, why you get such a sets, because those things are actually non-measurable, so you cannot like do using measurable sets that thing, but using non-measurable sets you can do. So anyway, those things are something like if you are interested you can try to read, but that is not like part of what we should be discussing now. So but yeah, about this John's lemma, axiom of choice, and well ordering principle, maybe I can tell that there is a famous quote, so which says that uh, the axiom of choice is obviously true because it like is very intuitive. And then so the quote says that the axiom of choice is obviously true. The well ordering principle is obviously false because that is very counterintuitive. And then the quote says that, and who can tell about John's lemma? Because John's lemma, it seems very like complicated. Like it says about this partial order set, if every chain has an upper bound, then it's a maximal element. So this is a somewhat complicated statement. So so the quote is a kind of joke that okay, these all three things are equivalent, but one looks very like obviously true. Other looks that it should be false, and the third one is kind of complicated to describe. So, okay, so now let me try to state the Han-Banach theorem, and then we will prove it. Okay, so first I'll state this a general version for vector space, and then we will see for norm linear space how to write that. So let V be a vector space, and right now we will take vector space over R. So we are taking V to be a real vector space, and let P from V to R be such that P of Tx is equal to T times Px for every T greater than 0, and P of x plus y is less than equal to Px plus Py for all xy belonging to V. So the second statement, the second thing is subadditive. P is subadditive, that P of x plus y is less than equal to Px plus Py. And the first one says that for positive scalar, if you multiply, then you get T times Px. So it is homogeneous with respect to this positive scalar. Such a P is called convex functional. So by assuming these two things, you can see that P is a convex function, because if you take P of say Tx plus 1 minus Ty, where T is between 0 and 1, then by the property 2 and 1, you will get that is less than equal to T times Px plus 1 minus T times Py. Maybe I'll just write that such a P is called a convex functional in V. So we are not saying that
So,
P of x is equal to T times Px for every T scalar T, only for positive. Yes.
so like, is property one true for every convex functional? Like, is property one, sorry, like, so these two
Not
properties will imply it's convex, but the
right.
first property is also something additional that
Yes, yes.
it's
So that is true. So I'm not saying that any convex function satisfies both these properties, right? So in fact, I mean, if you just assume convex, then it need not be subadditive also, right? So this subadditivity and positive homogeneity, these two, who if it is satisfied, then we call it convex functional. Is it okay? So it's we are not saying convex function. So it's convex functional. The definition is that if it satisfies these two properties, then we will call convex functional. And what I am saying is that a convex functional is always a convex function, not the
okay.
other
Okay,
way, right?
yeah, yeah, I get it. Thank you.
Yeah. So uh, so of course you should realize that you have an example of convex functional, right? So can you give one example for convex functional?
Any linear functional is also convex.
Yeah, so I mean, linear functional will obviously be convex functional, because it satisfies actually P of x plus y additive, and it is the homogeneous. And anything else which is not linear,
A norm.
yeah, very good. So if I have any like real norm linear space, then norm will satisfy these two properties, right? Because triangle inequality says that norm of x plus y is less than equal to norm x plus norm y, and norm of t times x is equal to mod t times norm x. But if t is positive, then mod t is equal to t. So therefore, we'll get t times norm x, right? So that is the, you should keep in mind that norm is the something which satisfies this, but there can be other things also, which is not a norm, but it can satisfy these properties. So later we will use it for norm to like get the Han-Banach extension theorem. But right now what we are saying is that we have any real vector space and P is a convex functional on V. And suppose W is a subspace of V. So let W be a subspace of V and let G belongs to W prime. So remember what is W prime? W prime consists of all linear functionals on W. So that is G from W to R is linear. Right. So if I take any linear functional on a subspace such that this G is dominated by P, so such that G of x is less than equal to P of x for all x in W, then this Han-Banach theorem says that this G can be extended to a linear functional on the whole space V. So then there exists, let's call F in V prime. So that means F is a linear functional on V such that F restricted to W is equal to G, and this F is also dominated by P. So Fx is less than equal to P of x for all x in V. So let's try to understand the statement again. So we have any vector space and P is a convex functional on V. And now if I have any subspace W and there is a linear transformation from W to R, so there is a linear functional on W which is dominated by this convex functional P. So G of x is less than equal to P of x for every x in W. Then we are saying that this G can be extended to a linear functional on V, which is also dominated by this convex functional P. So there exists F such that Fx is same as Gx if x belongs to W, and f of x is less than equal to P of x for every x in V. Is it okay? So let's try to prove this theorem and then we'll apply this to get the Han-Banach extension theorem for non-linear spaces. So we will do this in two steps. Step one. First, we will define a partial order set. So let P denote the collection of all pairs. It's called Y comma H, where Y is a subspace of V containing W and H from Y to R is linear. So I could have just said that H belongs to Y prime. Right. So P is consisting of all subspaces containing W and together with a linear functional on that Y. And also, so this is a linear map. So Y is a subspace containing W, H is linear, such that H restricted to W is same as G, and H of X is less than equal to P of X for all X belonging to Y. Right. So whatever properties we want, we are like putting all those things. So we want a subspace containing W and a linear functional which is an extension of the linear functional G on W, and it is dominated by this convex functional P of X, P. Right. And then now you should get an idea that what we will do is we will prove that this P has a maximal element. So basically what we want to have like Y equal to V. So we want V comma F belonging to this P. So that will mean that we want uh, that there should be some F which is linear functional on V, and this F should be extension of G, and F should also be dominated by this P of X, P. So we'll show a maximal element, and then we'll show that maximal element has to be whole of V. So that is how we will prove this. So first, what we'll see that so first of all, uh, this P is non-empty, since you can take Y equal to W and G. This belongs to P, right? So if you take the subspace W and this linear functional G, then that clearly satisfies all these properties. So we have that this is a non-empty set, and then we can define a partial order less than equal to on P by Y comma H is less than equal to Y tilde comma H tilde if Y is a subset of Y tilde and H tilde restricted to Y is equal to H. Right. So the partial order is that you have this Y should be a subset of Y tilde, and H tilde should be a linear extension of H. Right. So then we say that this element is less than equal to this. So you can easily check that this is a partial order. I'll just write that. It is easy to verify. This is a partial order on P. Now we want to use Zon's lemma. So for that, if we take any chain, then we have to show that there is an upper bound. So let's call C equal to some yihi I belonging to some index set lambda. This be a chain in P. So which means that this is a totally ordered subset of P. So if you take any two elements, then uh, we have that one is less than equal to the other, right? So if I take any chain, and here see this chain need not be a countable collection. So this I'm writing yihi, but this can be over an uncountable index set lambda also, right? So C is any chain in P, then we have to show that it has an upper bound. So what is an upper bound for this? So define capital Y equal to union of yi, I equal to I belonging to this index set lambda. So we are simply taking the union of all these subspaces yi, and let h from y to r be defined by h of x is equal to hi of x if x belongs to yi. So we know that because y I am taking union of yi, so I have to define for every x belonging to y. So if x belongs to y, then x belongs to yi for some I, and then we have hi which is defined on that yi. So I am writing h of x is equal to hi of x if x belongs to yi for some I. Right? What you need to see that this h is well defined. So that means that suppose x belongs to yi as well as yj, then how do I know that hix is same as hj of x?
Because either either yihi is less than equal to yjhj, or yjhj is less than equal to yihi. In either case, one is a restriction of the other, and
Yeah, very
so
good. So that is
uh,
the main thing, that
direct-
because we are taking a chain, so therefore we know that if I take x belonging to yi as well as yj, then we must have that one of them is a subset of the other. So suppose yi is a subset of yj, then we have that hj restricted to yi is same as hi. So therefore hj of x is same as hi of x. So that will show that this h is well defined. And what we now need, that this y comma h, this should be in P, right? So for that you need to also see that y must be a subspace of W. So in general, union of subspace need not be a subspace, right? But here what we are taking is that uh, these subspaces are such that for any two, at least one is contained in the other. So using that, you can prove that this Y is a subspace, and this H linear also you will have to prove, and then you have to see that this Y comma H is an upper bound, for this chain C, right? So these are the things that need to be verified. So, since this C is a chain in P, we can show that this Y is a subspace of V. H is well defined and HY to R is linear. Right, so we get a linear functional on a subspace Y, and because we have yi where such that this contains W, so of course this Y contains W. So clearly W is a subspace of Y. So therefore what we get is that uh, this Y comma H, and also if I look at H of X, this is less than equal to P of X for all X belonging to Y. Because if I take X belonging to Y, then X has to be in one of Yi, and then H of X is defined as Hi of X, and we know that Hi of X is less than equal to Px, so therefore H of X will be less than equal to P of X. So therefore this Y comma H, this belongs to the partial order set P, right? So Y comma H belongs to P, and Yi Hi is less than equal to YH for all I in lambda, right? Because Yi is clearly a subset of Y, and the H restricted to any Yi is same as Hi. That is how we had defined this H. So therefore we have this less than equal to. So this implies that this is an upper bound. So therefore every chain in P has an upper bound. So by the Zorn's lemma, this P has a maximal element. Let's call say Z comma F. So we get a maximal element, but what we want to in this Han-Banach theorem, we want that there should be a linear functional defined on the whole vector space V, and this F should be dominated by P. So what we want is that so we want to show that this maximal element Z comma F, this Z has to be equal to V. So this is step 2. We will show that this Z must be equal to V, and that will prove. the theorem, right? So which will complete the proof. So this is again not a very easy thing how to see that this has to be whole vector space. So for that, what we have to show is that suppose this Z is a proper subspace of V, then we have to see that we can extend this. So we get a bigger element, right? So that will contradict the maximality of this Z comma F. So suppose this is not equal to V, then we will see that we can get a bigger element. So for that, what we have to see that if suppose we have a linear functional on a proper subspace, then we can extend it to a bigger subspace. So how to do that? So suppose this Z is not equal to V, so then there exists some X naught in V such that this X naught is not in Z. So we get an element which is not in this subspace Z, then we will see that we can extend this linear functional on Z to a bigger subspace. So what is the subspace we will take? So consider capital Y equal to X plus T times X naught such that X belongs to Z and T is a real number. So basically we are taking the subspace spanned by Z and this X naught. So this is the subspace spanned by Z and X naught. So then this Z is actually a subspace of codimension 1 in Y, right? So we are increasing the dimension by 1. Though Z can also be infinite dimensional. So this basically Y quotient Z, if you see, that is one dimensional. So this is called Z is a subspace of codimension 1 in Y. So we look at this subspace and then we will try to define a linear functional on this Y, which is also dominated by P. So we will define some H belonging to this Y prime such that H, let me simply write this Y comma H, this belongs to P. So we want a linear functional on Y, and this belongs to P means that this H of X will be less than equal to P of X for all X in capital Y. So this will contradict the maximality of ZF. Right, because here this Z is a proper subset of Y. So therefore this I mean ZF is not equal to YH, and we have ZF is less than equal to YH. So this will uh, Yeah, we also want that this H should be an extension of Z. So H restricted to Z is equal to F. So we need to define a linear functional. So we define H of any element in Y is of the form x plus t x naught. So H of x plus t x naught, because I want it to be linear, this has to be equal to h of x plus t times h of x naught. So h of x, because x is in z, so h of x we want to be equal to f of x plus t times h of x naught. So h of x naught we want to be equal to something. So I'll write this is equal to some scalar. So this is equal to alpha times t for x belonging to z and t belonging to r, where alpha will be chosen suitably. So we will choose the alpha in a way such that it satisfies that this H is dominated by the convex functional P. So what we want, we want this fx plus alpha t, this should be less than equal to P of x plus t x naught. Right, because this is my h of x plus tx naught, and we want that this should be dominated by p. So this should be less than equal to p of x plus tx naught. This should be true for all x in z and t belonging to r. Now if t is positive, then we know that this px plus tx naught, this is less than equal to px plus p of tx naught, and p of tx naught will be t times px naught. So if alpha is positive, then p of x plus tx naught, this is less than equal to px plus t times px naught. So we would get this alpha such that this fx plus alpha t is less than equal to px plus t px naught for all x in z and t positive. So if we get this, then we will get this for t positive, and then we have to do for t negative also. So this is equivalent to, if I write, if I divide by t, then we get f of 1 by tx plus alpha is less than equal to p of 1 by tx Okay, I think I am out of time, so let us stop here. So I'll finish this tomorrow, and then we'll see the other Hanbanach theorems.